Hi everyone, Dr. P here, and coming to you from my iPad. I wanted to do this on the iPad so I could basically mark up the PDF of the um, the criteria for determining SN1 versus SN2 versus E1 versus E2. This is from David Klein's text, and it's got several parts. I know I showed you guys this briefly in class. So we have here in the first table just some examples of strong bases that are weak nucleophiles. These are our non-nucleophilic bases, so DBU, DBN. Talked about those a couple of lectures ago. Strong bases that are also strong nucleophiles, hydroxide, methoxide, ethoxide. Weak bases that are strong nucleophiles, the halogens, except for fluoride, RS minus, HS minus, RSH, H2S, and some weak bases that are also weak nucleophiles, H2O, methanol, ethanol. Now again, this list is not exhaustive. You should go back and take a look at a previous lecture where I talked about good nucleophiles, because amines are strong nucleophiles. Actually, they're depending on the amine, they could be a reasonable base. There's a lot of different examples. Like 2-butoxide is kind of in between here. It's a strong base. It's not as nucleophilic as these guys, but if you have a primary alkyl halide, or say a methyl halide, rather, the 2-butoxide can react with it. All right, so one of the tables that Klein provided this is from the third edition, is the following one here. And so this table, this matrix if you will, has a few different things on it. We've got the, okay, yes, black is what I want. Okay, substrate, whether it's primary, secondary, or tertiary, and then we've got the base slash nucleophile. Okay, so substrate, primary versus secondary versus tertiary, and then the four categories of base slash nucleophile. Notice some interesting things here. If you have a strong base that is not a nucleophile, you get an E2 reaction. Boom, that's it. If you have a strong base that's also a strong nucleophile, but you have a tertiary alkyl halide, then you'll get an E2. SN2 and E2 will compete if you have a strong base that's also a strong nucleophile. With primary substrates, SN2 is major. And with secondary substrates, the E2 is major. So let me add that in here. So we'll just say here major, E2 is major. Now, if your nucleophile is not a good base, then you'll get SN2 with primary or secondary substrates. And with tertiary, because the SN2 is so slow, you'll get an SN1. Lastly, if your base slash nucleophile is weak all around, you won't typically get reactions, or they're not that useful, and we'll talk about this in a minute or two. You won't get reactions with primary or secondary substrates. With tertiary, you'll get a mix of SN1 and E1. And so the E1 will actually be favored by heat. So if you have, let's say, methanol, solvent, you react your tertiary alkyl halide in it, and there's heat, then that's going to favor E1. If there's no heat, then it'll probably favor SN1. Okay, we can look at this in a little, whoops, There we go. We can look at this in a little more detail here, and that's the next couple of pages. And I have a file posted, which is this page and this page just in one page if you wanted to print that out or something, but the text is kind of small. And this is from an earlier edition of Klein, and what it goes through is looking at things kind of in order. First, looking at the reagent, that is nucleophile or base. Then looking at the substrate, and then what mechanism do you get? And then, and this is what I think is really nice about this table, and it's worth reading these. Worth reading these little descriptions. They're not that long. But it talks a little bit about why you can get these different products. So let's say we had something that was just a good nucleophile. So SH minus, Br minus. With a primary substrate, we get SN2. With secondary, we get SN2 and SN1. And with tertiary, we get SN1. Okay, now let's go back here. Whoops. And we actually saw that they just said SN2 here. So that's something that's a little bit different. Well, let's read what it says here. When the reagent functions exclusively as a nucleophile, only substitution reactions occur. SN2 predominates, and for primary, SN1 predominates for tertiary. For secondary, both can occur, although SN2 is generally favored, especially when a polar aprotic solvent is used. So that's a case where you're going to look at all of your conditions. I'll do some practice problems. I'll have an online workshop and do some practice problems. So you figure out your nucleophile, you look at the substrate. So it's like, all right, I got Br minus, I got secondary, so it's either SN1 or SN2. Ooh, let me check the solvent. Oh, I've got DMSO, that's polar aprotic, boom, SN2. All right. If you have something that's only a base, like DBN or hydride, you're going to get E2 all the time. Okay? And it mentions that the mechanism isn't sensitive to steric hindrance, and you get primary, secondary, tertiary. You still get the reaction. If there's possible different products, Hoffman versus elimination, Zaitsev products. Something bulky would give you Hoffman. Something small like H minus would give you the Zaitsev. Okay. Whoops. There we go. Let's see. Next we have something that is a strong nucleophile and base, and this is where you get both E2 and SN2. But notice they're all the second order, all the bimolecular reactions. Primary gives you SN2 as your major, secondary gives you E2 as your major, tertiary gives you E2. Okay, and it mentions here, for primary substrates, SN2 predominates over E2 unless TBU-OK, so the T-butoxide, is used as a reagent, in which case E2 predominates. And that's because T-butoxide is a hindered base, so it's not as good a nucleophile as, say, hydroxide or ethoxide. And then it mentions here, you can read about this, secondary substrates, why E2 happens versus SN2, and then tertiary, why you would only get E2. All right, now the last case here is where we have something that's weak all around. So alcohol, water. And if we try to get a reaction with primary substrate, in theory we would get SN2 or E2 because it's a primary substrate. The carbocation, primary carbocation, is just not stable enough to do one of the first order reactions. However, it is not practical. Why is it not practical? Because the reactions are too slow. And that's why there was that big red X here. Now, if we had a secondary substrate and a weak nucleophile/base, we could get any of the four possible reactions. With the secondary substrate, the carbocation will be, reasonably stable, not as stable as the tertiary. And it's also not as hindered, so we could get SN1 or SN2, but we could also get E1, E2. These are also not practical. Again, because the reactions are too slow and too many products are formed. There is an exception, however, which is a secondary alcohol will undergo an E1 reaction when treated with concentrated sulfuric acid and heat. That is a dehydration reaction that we saw back in chapter 8. So, you can get the dehydration. It wasn't in chapter 8. Chapter 8, we saw the hydration. But this is essentially the reverse of the hydration. Remember, hydrating a double bond, we used dilute acid. If you use concentrated acid, you can get the E1 reaction to go. Then lastly, with tertiary, we're going to end up with SN1 and E1 competing. Once again, as I mentioned before, high temperatures are going to favor E1. So definitely take a look at these files. Go ahead and read these little descriptions, and try to be very familiar with this. When you're working on the practice problems, go ahead and have this with you. So that you can, maybe have this on your phone if you're working on your iPad, or if you're working on pen and paper, have this on your tablet, whatever. But yeah, have it next to you while you're working on practice problems until you get to the point where you don't need to keep referring to it. All right, well, that wraps up all the lectures for chapter 10. 11. 10 lectures for chapter 11. And I will see you guys later. So until next time, stay safe out there. Bye now.